Okay, I'd like to get things started. The homework 3s are here. They will be here after class, so you can pick it up then. But I'd like to get us started so we finalize everything for the midterm. For the midterm, which is going to be next class, there are going to be about 5 problems on the midterm. It will be on graph algorithms, backtracking, and dynamic programming. Who here has a last name beginning with I, from I through R? Okay, if you are beginning with I through R, then you are going to be in the auxiliary room to take the midterm next time. Okay? The people who took the auxiliary midterm in there, you come here this time. I through R. Go to the other room, which I believe is Social and Behavioral Sciences 328.
Does that count R?
R counts, yes. I counts. Those are going to be in Social and Behavioral Science, room 328, and all this is on the website now. Okay? Any questions about that? Any questions about the midterm? Okay, I'd like to close up access on the homework for now, so hold on. Okay, go. No. No. Okay, cover it now. Okay, fine. The homeworks will be there if you want them later. Okay? Any questions about the midterm? Let's start to settle down. Any questions about the midterm before we go on any further? Okay? Any questions? Yes? Okay, everybody a little quieter now. Come. No rubble now. Will there be implementation questions? There will not be anything where I'm obviously going to ask you to write program in a language. So you're not going to be given a terminal or anything. On the other hand, an algorithm problem in the book that said implement, if you want to, I may ask you to describe how to do it in pseudocode or something like that. Certainly backtracking problems are going to be allowed, and in fact I will tell you there will be a backtracking problem. And so it would be good to be able to understand how to take your problem and break it down into the way we have done it in class. Construct candidates, process solution, is it a solution? Okay? And show that it goes through and generates those things. Any questions about anything on the midterm? Yes? Will you have to deal with optimizing backtracking? I think I would probably say it's fair for me to ask you something that's correct. It's a little hard for me to judge, looking at your algorithm, whether it's better or not without running it. So the important thing there is going to be correctness as opposed to being clever in pruning. Okay, so I'll give you something. I will say, generate this using backtracking. That I think I can probably say. Yes? It covers chapters 5 on unweighted graph algorithms, chapter 6 on weighted graph algorithms, chapter 7 on dynamic programming, and chapter 7 on backtracking, and chapter 8 on dynamic programming. Yes? There is no midterm 1 stuff. Okay? I mean, implicitly, you still are assumed to know how to sort, and you're still assumed to know how to use a data structure if you have to. Okay, but there is nothing explicitly testing from midterm 1 stuff. Any questions? Okay. Okay, so what I would like to do is, yes, question. Homework 3 is posted, yes. Oh, yes, homework 3 solutions are posted. Has anybody seen that? Yes, it is posted, okay? I would encourage dynamic programming people to look at homework 5, which is also posted, so that you can look at the dynamic programming problems that are there. That's on your homework, okay? And those are probably a good practice for the midterm, okay? Any questions? Yes? Yeah. So physically bring your programming. If you're turning in your homework 4, then turn it into whichever room that you are assigned to. give it to the proctor of that room before class starts, okay? Again, if your names are between I and R, last name begin with I through R, you are exiled to this smaller room for the midterm. Okay, that is Social and Behavioral Sciences 328. Okay? The A through H people were assigned there for the first midterm. The rest of you people will be in there for the final. Okay, so it's all going to work out evenly. But I through R in the other room. Any questions about it? Okay, what I'd like to do is to finish up on dynamic programming today. And maybe if we have some time, talk about, if there's any other questions about anything we've done. But I'd like to talk about the daily problem today as a representative of what we do with dynamic programming. And the problem of the day today, if I'm correct, had to do with dropping eggs from a building. Is that correct? Okay, so let's make sure we understand what the problem is, and then we can do it. Here is a building, okay? It has n stories, okay? Here is an egg, okay? All eggs, are pretty much the same, okay? And they have a property that when you drop them from a particular height, they will break, right? So we would like to figure out what floor from the building is it that represents the threshold where if you drop it from below that height, the egg survives, and if you drop it from above that height, the egg breaks. Does everybody see what the problem is? Okay. Now, we are given a building with n floors, and we are given, let's say, k eggs. And what we would like to try to figure out is, what is the smallest number of tosses we need in order to figure out the height of the break-no-break transition? Any questions about that? Okay? So let's think about that. If I give you one egg, what is the right way to find the threshold? Okay, yes, you. Start from the bottom here and say, does it break? No, 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 ooh. Okay, because you now got a messy yolk on the ground, right? Why did he go from the bottom of the building to the top of the building? Why didn't you start from the beginning? Yeah? What?
If you start from the top, it might break, then you have no idea.
Right, if you drop it from here, you've got a broken egg, you have no idea of what the transition is and no ability to ever find out, right? Any questions about that? So does everybody agree that if you want to think about the worst case, let's come up with a function. Let's say that we want to figure out the number of tosses we need. T as a function of n and k. T of n floor building with one egg. How many tosses do you need to find out the height of the building, yeah? N, because you may eventually not break till the last toss. And maybe you'll even learn it didn't break when you tossed it off the building, right? So does everybody agree that if we define TNK as being the number of tosses needed to find the transition in an n-floor building with k eggs, right? Now, what if you have a lot of eggs, okay? As many eggs as there are chickens, or something like that. As many eggs as you need. What is the right way to figure this out? Yes?
You can kind of implement something similar to like a binary search, but on the building's height.
Does everybody see that you take your carton of eggs and you climb to the midpoint of the building and you toss one out? If the egg broke, you go a quarter of the way down the building. If it stayed up, you go through this. Does everybody see that? So that also tells us that we know that T sub nk of that is n. T of n, if you give me log n eggs, I can get away with log n tosses. Okay? And that's clearly the best you can do, right? Now, what if I give you 2 eggs? Let's start to think about it. How can I use 2 eggs effectively here? Okay, yes?
I would drop the first egg at the midpoint of the building, and depending upon whether or not it broke, let's say it breaks, then we have 1 egg, but we only have to search half.
Okay, you're saying that okay, so if he uses 2 eggs and tosses it at the midpoint of the building, then if it breaks, he's learned what? He's cut down his building by 1/2, okay? And, now he's going to have to do the linear thing because he's only got 1 egg left, right? In the worst case, he's going to use something like n/2 tosses. Does everybody agree with that? Is there a better thing you can do with 2 eggs? Okay. Yes.
You can drop the egg on floor 1, 4, 9, 16, 25.
Okay. 1, 4, 9, 16, 25. Okay. So what is he doing here? Is he doubling things? No, he's not doubling things. What is he doing? He is squaring them. Why is he squaring them? Well, I don't know exactly. I may know, but not completely sure. But now, what are you going to do now?
So you're going to have to be searching at most the square root of n. Once it breaks, then you know that it's between 1 and another square.
Okay, so let's think what he's doing that is right and maybe is... actually, let's think about what he's doing right, and I'll tell you how I would think about the same idea a little simpler. Okay, or at least simpler to me. What he's saying here is he's going up by a square here, and likewise, because he's testing the thing from smallest to biggest, okay, he's not going to break an egg until he knows within 2 squares that the floor has to be within a square, 2 squares, right? Okay? Any questions about that?
I'm not sure if it's right, but wouldn't it possibly, when you get to the bigger numbers, be more efficient just to segment the building by an even amount?
Okay. People are now using all kinds of special properties of squares and buildings and things like this, okay? What I think he's trying to do, and he might be doing the right thing actually, okay, because I'm it's a mental what I want to do instead is, suppose I do the same thing he's doing, except I break it into I find out what square root n is, okay? And I do it at the square root nth floor, the 2 square root nth floor, the 3 square root nth floor. What is the nth floor equal to? That's the how many square root nth floor? Square root n, square root nth floor. Does everybody see that's what it means to be n? Okay? So suppose we now go through this procedure. It would go, fine, this is where it would shatter, right? Does everybody see that there's now a gap here of size square root n, right? We have 1 egg and something of size square root n, okay? We could now find, by doing our regular walk up here, in at most square root n more steps, we would know what it was. Does everybody see that? That's sort of, I think, the idea. Well,
It's totally wrong.
okay, if it's totally wrong, then fine. But he's still got squares, he's got square root n's here, okay? So what's interesting about this? I have just proven that I can do it with 2 eggs in 2 times square root n tosses. Okay, let's just see if we understand. How many people understand this? Okay? Any questions? People see why 2 square root n suffices. Does anybody want to know? Yes, question.
I'm not completely sure on that.
Okay, so let's think what we're going to do. By sampling every square root nth floor from the bottom, suppose it was a 100-story building. I'm going to start on the 10th floor, then the 20th floor, then the 30th floor, and keep tossing my egg until it breaks. Then I know to within 10 floors of where it has to be. the transition is, correct? And now, if I then start on the 10th floor and go to the 11th floor and toss it, 12th floor, 13th floor, I will find where that transition is. Okay? And since the gap here of square root n is exactly equal to, is exactly square root n, and n is exactly equal to square root n times square root n. There were square root n steps on the first round and square root n steps on the second round. Yes?
Well, what if, let's say, the minimum floor it needs to break is 4, and you started out at...
If the minimum floor was 4, what would I have done? I would have tossed it out on the 10th floor, say, ew, it broke, and now go back to the first floor and try it. And then the second floor, and the third floor, and the fourth floor, and that's where it broke. So I used at most square root n steps to figure out a round of square root n that were enough. How many people see why this is order square root n? Okay, that's good. And people see that's better than your square root n over 2, right? So you were originally saying n over 2. But is this really the optimal way to do it? Okay? Is it possible there's a better way to do it? Okay? And let's use dynamic programming to figure out the right way to do it. Okay? What is the right way to figure out what to do with my egg? Okay? If I have n floors that I am worrying about, okay, and I have k eggs, and I have a magic formula that will tell me the exact number of the minimum number, possible number of tosses needed to find, okay, the transition, okay, given that I've got these eggs, suppose I have something that will tell me what the minimum number of tosses I need is for any n and k. Can I use this to try to find where the right toss is? Okay, we have some special cases we know the answers to, right? Okay? So where is the right place to toss the first egg? Or equivalently, can you come up with a recurrence relation to decide what this is, to compute this? Okay, let's think about that. Any ideas? Okay. Any ideas what the minimum number is? We want to figure out what the minimum number of ways is. If you think about it, what we want to do is, I think we want to toss the egg on the floor that will minimize what our time is going to be, right? What floor is that? It's the xth floor. Okay? What is x? Well, by definition, it seems to me it is the minimum from 1 to n, okay? It minimizes the total cost of egg dropping. What happens when I toss an egg out on the xth floor? This is floor x. What is going to happen if I have n floors and k eggs to toss? What are the things that can happen when I toss my egg out on the floor? That X floor. Yeah?
Well, it can either break or not break.
It can break or it cannot break. Suppose it breaks. What has happened? What is my state of my knowledge now? Okay? Yeah? Somebody? I certainly now, if it breaks, there's two cases. There is it breaks or it doesn't break. Basically doesn't break. And we agree that if it breaks, I have k minus 1 eggs, and if it doesn't break, I still have k eggs, right? How many floors do I have left? Okay, let's think about it. Depends upon the problem. Yeah? If it breaks, what do I know? If the floor broke, if I tossed it on the x floor and it broke, how much is left? X. I now know that somewhere between here and here is the transition. Does everybody agree with that? So if I toss it off, we know that at some level it will not break, right? There exists a height that you can toss the egg and it doesn't break, right? Then we want to know that if x is too big and 0 is too little, somewhere the answer lies between 0 and x. Does everybody agree with that? So, if it did break, we have a effective building of size x left anymore, and k minus 1 eggs. Does everybody see that? And what's the best possible way to do a building with? What's the number of steps you need in a building with x floors and k minus 1 eggs? T, okay, because T sub nk is defined as the minimum number of ways to do that, right? So everybody see, this is what happens if we toss an egg and it breaks. This is how much work we have left to do. Yes?
Also, we have to add the 1 because we already tossed an egg.
Okay, you're telling me that we didn't actually toss an egg here. So we are going to have to play 1 someplace else. Let's say 1 plus. That much is probably true, right? Okay? How much work do we have to do if I tossed a thing egg out and it goes thunk and it didn't break? Okay, yeah? Now I have a building left where my undeciding thing is between n and x, between the nth floor, x floor, and the nth floor. So it's like having a building of height n minus x now, right? Does everybody see that the non-broken egg tells me that anything interesting has to happen between x and n, right? Which is only an n minus x floor building, right? How many people see that? That if the egg doesn't break, my problem is left as a problem on an n minus x height building, yeah?
Sorry, what was the plus 1 for?
That is the cost of paying the egg. Actually, maybe we'll put it out here, in fact. I want to put it out here. 1 plus. This is the cost of that egg. I am actually tossing that egg out on the x floor. I have to pay for that toss, right? Okay? Yes?
So on the n minus x, does that take into account the fact that it's 5 floors that are higher up, and if you started 0 to 5 versus...
You're saying, does it make any difference that it's higher up? Okay, it makes difference if the building doesn't have an elevator, because it's a lot of stairs to climb up. Okay? But no, again, my problem, if I want to try to figure out the uncertainty, it's no harder to figure out if you don't pay the cost of climbing up the stairs, it's no harder to find out whether it breaks between the 90th and the 100th floor than it does between the 0 and the 10th floor. Does that make sense? It's the same level of uncertainty you have here, right? Okay? Any questions about that? People see that? So let's figure this out. This is what happened. The cost is if it doesn't break. Okay? This is the cost if it does break. What is the worst case if I toss it off on x? Okay? Yeah? What is the worst case for a given x? Okay? Is it if it breaks or if it doesn't? You say breaks? Depends on x. Okay? If it broke on the first floor, that'd be the greatest of all possibilities, right? Then I knew the transition had to be a 0 or first, right? But on the other hand, it depends. So which one of these is the worst? I'm going to say take the max of this, comma, this. Okay? Now let's think about what this is saying here. Okay? Let's talk about it. Again, I'm hearing some rumbling in the background. Okay? But let's talk about it. Okay? The minimum number of steps it takes, if I have to find but distinguish among n floors with k eggs, is, for some x, there is a best place to toss it out. Okay, which is the x? Well, it's the one that minimizes the total cost. What is the total cost? Okay, it depends upon balancing in some sense. What happens when when it breaks and when it doesn't? It would be bad to be too conservative and move up just one floor and say, it won't break, thank goodness I saved that egg. Right? It would be bad to be too bold. Say, I'm going to go right to the middle, okay? Because I have an infinite number of eggs. If you don't have an infinite number of eggs. Right? But it should be clear that what you want to do is to toss it off on the floor that minimizes the worst case. And the worst case is the number of steps if it breaks at that floor, and the bigger of the worst case of it breaking on that floor, and it not breaking on that floor. Does everybody see that? And so this is what the recurrence is doing. Okay? We're going to try to drop it off. It's going to be, the minimum number of tosses I need is 1 for the toss on the X floor. And then once I have tossed it at the X floor, I will pay the bigger of the two halves of my problem that has to be done. That's why I've got a max here. And depending upon what X is, the bigger part of the problem might be if it broke, might be if it didn't break. And I want to minimize globally what it will do. How many people see this? Very few. How many people don't see it and want to see it? A couple people, okay, more than usual, okay? But let's think, what are we doing? Why in binary search? Let's say you're trying to find somebody in the telephone book, okay? Why is it that we look in the middle of the phone book, okay? Why do you say, I feel good about it, maybe I should look near the end? Why is it that you don't look in the Z's? Okay, yeah?
Because of our friend's name isn't 666, something like that.
Because the worst case is bad if you have looked at the Z's. Does everybody see that? That is what we do with binary search. We are going to be taking a look at putting on where do we decide to look next. Okay? We look where such that our worst case is going to be as small as possible. That's why we like binary search, right? And the reason is if we slide over here, if we get lucky and we're told that it's above here, we won. We're now looking over a smaller region, right? But in the worst case, you don't get lucky. In the worst case, they're always out to get you, right? And so if you didn't look at the middle point, the point where the worst case was as small as possible, you would lose. Does everybody see that without binary search? Likewise here, we have a freedom to toss off our egg at any floor we want. And the one we want to toss it off in is the one that, if we are as unlucky as possible, okay, it still isn't going to be that, it's going to be as good as possible, right? Which means we want to toss the egg that minimizes the worst case time, which is the bigger of the time if it breaks and the time that it doesn't break. Okay? And if you see it like that, this is a logical, straightforward thing. Any questions about that? Okay, any questions about this recurrence? Okay? Let's think about it. Any questions? Okay, and what's interesting is if you do this, if you gave it for one egg and evaluated it, it would figure out the linear search. And if you gave it log n eggs, it would figure out the binary search. Because it's going to figure out the best place to toss the egg given your situation. Okay? Any questions about that now? Okay? Any questions about this? What is the running time of an egg optimum? Now you want to actually figure out how to do it. You got to record. What basis cases do we know? Let's think about it. Are there any other basis cases we need to know? Okay. Yeah?
I guess if k equals 0, it's...
So k equals 0 or k equals 1 I kind of like, is a basis case. What if n was equal to 1?
then we just need one toss.
Right, so does everybody see that if I have T of a one floor building and I've got k eggs, no matter how many eggs you can't help me, right? Does everybody see that's the other basis case, right? For a short enough building, more eggs doesn't help you, right? Any questions? Yes? Okay, so let's think what we want to do. So it depends, I guess, upon, well, if I have a one-story building, the question of whether it breaks or does not break is still interesting. Yeah. That level of uncertainty would require a toss. Okay? So we could take a look at that. You might say that for a zero-story building, okay, no matter how many eggs you have, then you don't know anything, and that might be 0. Right? Okay? Any questions about it? Yes?
Wouldn't that be a problem if like you had a very short building and your red end was actually 1, so you went to the top building on one of the recursive calls? You wouldn't necessarily want it to be 1 because you want to test that floor first.
Wait, no. So what is my problem?
If you have like a 2-floor building and you're doing red end, you'd have to check each building during the recursive.
If I had 2-floor building, and what are my possible outcomes? One is that it will break on, okay, so if I have a 2-story building, there's a question of, does it break on the ground floor, the first floor, or the second floor? Okay, these are the 3 possible outcomes, right?
Wouldn't you make a recursive call to one of them where you were on the second floor and you only had one option for n?
Okay, it might pay, depending upon how this works out, depending upon how many eggs work out. I don't know if it pays for me to start on the first floor, the 0th floor, or the second floor, right? This recurrence will tell me that. I don't know if that answers your question or not. Maybe it doesn't. Let's try again.
Yeah, so I was thinking since it wouldn't, in this situation, if it wouldn't break on the second floor, you would check.
If it wouldn't break at the second floor, if all I have is a 2-story building and I toss that egg and it doesn't break, I have to decide the egg is indestructible. I don't have any bigger building. I don't have anything else I can toss the egg off of, right? At that point, I say the egg has won. Okay? So that's in this problem. Okay?
Right, but wouldn't you make a recursive call to Tn minus x? And
what I'm going to do is, again, the same thing I'm going to do here. My choices are, I can toss it off on the 0th floor, the first floor, or the second floor. The decision of which one I want to do, I want to pick the one that will minimize my maximum remaining amount of work. The remaining amount of work is if I toss it off on a particular floor, either the egg will break or it won't break. This is going to tell me how much work I have to do in each case. I'm going to toss it out on the floor that minimizes my maximum amount of remaining work. And that is what this is doing. Any questions about that? Okay. Any questions about this? Okay. So think about this. Again, it is another example of a dynamic program, and I saw people getting ghastly, oh my God, min of max. But if you think about it, it's logically what we're doing, right? We want it, min is saying pick the best place, where the cost is governed by the worst of the possibilities. Okay? And then this expression, I think, is a straightforward interpretation. Yes? T0, if I have a 0-height building, how many tosses does it take? You have to decide, does it take 0 or 1? Okay? it depends whether you know whether or not tossing it out of a zero-height building breaks it or not. If you have to learn that the first time, one egg may have to go down. Okay? Any questions? Okay? Yes? How do I implement this recursively? Well, first of all, implementing it recursively is a snap. Okay? Because how do I write it recursively? My procedure is T. And to do T, what am I going to do? I'm going to call. It's just written just like it's written just the way that it is, right? This is a recursive program. T is depending upon 2 calls to T. Okay? Writing a recursive program like this is every bit like writing a Fibonacci numbers program, right? Now it's going to be every bit as slow as your Fibonacci's program if you wrote it recursively. But do you see that this is how to write this recursively, or do I need to be more specific about that? You got that? Now the other question is, what is the complexity of this as a dynamic program? Suppose we did this with dynamic programming. What would be the running time of this thing? How do I count it? It's the number of boxes times the cost to fill each box, right? How many boxes are there here? Okay. If I have an n-story building and k eggs, how many boxes do I have? N times k. My possible calls are a number between 0 and n, and 0 and k, right? So I've got n times k boxes. How much time does it take to fill in the box? Well, once this is sitting in memory, because this is a smaller problem, and this is a smaller problem, this takes constant time to retrieve, the max of 2 things takes constant time. It is going to be min over n things. This is going to run n times k boxes, k time per box. This would be an order n squared k algorithm. Any questions about that? Yes?
So isn't the binary search method better?
The binary search method is better if you have a lot of eggs. Okay? But if you don't have enough eggs, okay? You're casually, let's say you have 2 eggs, okay? And you stride into this building and you toss it off at the middle. If the egg breaks, you're out of luck. Do you see that the binary search is only an appropriate reaction if you have enough eggs to back it up? If not, you're being too brave, okay? So you don't want to put all your eggs in one basket, literally, okay? Yes? If you have 1 egg, the linear method is best. If you have an infinite number of eggs, the binary search is best. If you have a medium number of eggs, something in the middle is best, and I'm not clever enough to figure out exactly what it is, but I am clever enough to figure out this recurrence, and it will tell me where to toss off my first egg. And once that is done, once I have figured out, I see it's either broken or not broken, it will tell me where I toss off my next egg. Okay? Yes?
But the square root of n thing was n to the 1 over k, right? Wouldn't that always be better than n squared times something that's making...
No. Now, okay, so you're now saying, wait a second. If I generalize my binary, my square root n thing, you're telling me that I can get away with order n to the 1 over k eggs, tosses, right? This is saying I can get away with the optimal number of tosses if I spend this much time to compute. Do you see what the issue is different? Okay? Log n is how many tosses I make. Okay? Or n is the number of tosses I make. Right? If I want to minimize the number of tosses by finding the most deviously clever floor to pick it on, by spending this much running time, I can find the best place to toss my eggs. Okay? And you see what the distinction is. This is an analysis of eggs. This is an analysis of running time. Okay? Any questions? Any questions about the eggs problem? Okay? Going once. Going twice. Okay, good. So let me now try, if I picture what you guys are thinking now, okay, again, you've got various concerns about dynamic programming. Part of it you're saying is, you haven't quite gotten it yet. And part of it, though, may be in your mind that, that this still sounds, this sounds like we're working on pretty silly toy problems. Nobody's tossing eggs off of buildings. Nobody's cutting strings into sticks, okay? Let me now show you a real dynamic programming problem. Real meaning practical thing people paid money for, okay? Or should have paid money for, okay? Something that gets solved by a real simple dynamic program, okay? It is one of my war stories in the book. And it has to do, but I want this to be an example again of a application that's for real. And if you understand the application, you'll see that the program is really very simple. The dynamic program, the recurrence is very simple. Okay? And it has to do with two-dimensional barcodes. Now, this is a two-dimensional barcode. If you look at your New York State driver's license on the back of it, there is one of these things. Okay? And what is that thing? That contains your prison record and other details about you. So that when a policeman takes your driver's license, they go back to their car. You've been hauled over for speeding, okay? They take your driver's license, they haul you back, the driver's license back to the car, and they scan it, and they figure out whether they're dealing with a bad dude or not, okay? That's really what it's about, okay? The policeman wants to know, is this car in front of me being driven by somebody who's dangerous or not? And that's nice if you could put all the information about somebody's prison record in an easily scannable form on their driver's license. That's why you have it on the back of your New York driver's license. Okay? So the question is, how do you fit, okay, several hundred bytes of text in something easily scannable that can be in a, on a driver's license that people crumple up and they put in their pocket and they don't clean and it's dirty and all this kind of stuff. That's why you have a barcode. It's a reliable thing to scan, okay? And you want it to store more than the barcode on your can of beans. That only tells you a parts number, right? You want to be able to put some real text, several hundred bytes, 1,000 bytes worth of text on the back of your driver's license. Any questions about why the barcode is there? Okay? Now, what was the problem that they faced? The company doing it, which is now Motorola. I don't know, maybe you've seen Motorola. I think they're on like exit 62 on the expressway. They developed there's a question now. If you have a barcode that can store, let's try this thing here, kabunk. If you have a barcode that can store, let's say, 1,000 bytes worth of information, what is the right way to use those bytes of information to store text? And they developed the following kind of data compression scheme that is part of the official PDF 417 barcode standard, which is that they broke the letters on a keyboard into 4 sets. The capitalized letters, the lowercase letters, certain mixed letters, both upper and lowercase, okay? And other things like punctuation and stuff like this. Maybe digits would be part of the mixed. I don't remember exactly what was assigned. But every letter on the keyboard is assigned to some of these modes, but not all of them. If we wanted to do all the, let's say, all the letters in an ASCII, let's say there were 128 letters in printable ASCII, that would normally mean you needed 2 to the 7th bits, 2 to the 7th was equal to 128. That meant that you needed 7 bits per letter. Does everybody get that idea? But suppose, let's say, that instead you were in what we called capital alpha mode, and there were only, let's say, 32 symbols in the alpha mode. If the next letter was going to be something that's in capital alpha mode, to transmit one of those 32 possibilities might be only 2 to the 5th or 5 bits. Okay? Does everybody get the idea that what we're going to do is we're going to partition the letters or map certain letters of the alphabet to certain modes? Lowercase was A, B, C, D. Maybe we'd like to blank in all of them because blanks get used a lot. Okay? But what we'd like, what their idea is, understand the idea that if you have the letters broken into groups, and if you're likely that the next letter you're going to be is in the same group as your previous letter, then you only have to use the log of the number of letters in the group's bits for the next one, instead of the log of the whole character set. How many people see what I mean by this? This is what the iPad does on its keyboard, right? What happens when you are given a keyboard here? You're given only a small number of letters to type, right? I think that only A through Z appears. And how do you get a number? What do? You hit an escape key, right? And now the keyboard with the numbers come up, right? And then you stay in that until you shift back into a different mode. Do people know what I'm talking about here? Right? And why is it that they put the letters together on one keyboard and the digits on another? It's because usually you're typing English word, English word, English word, hit return phone number, digit, 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 right? As opposed to some mechanically generated, A76329 5Q XR. That's hard to type in that scheme because you're shifting between keyboards. Does everybody see what I mean? So if you have the problem where you have different sets of keys in different modes, just like your iPad keyboard does, okay? And if you have commands you can use to shift into another mode permanently, or maybe have something that's sort of like on a typewriter keyboard. On an old typewriter, you had 2 keys. There was a shift key, which would give you a capital now, and a shift lock. Do people remember the shift lock key? Yeah? That meant everything you're typing from now on was a capital letter, right? When you hit shift lock, you moved from lowercase mode into alpha mode. And to get out of it, you had to hit the shift lock button again, right? Whereas if you just hit shift, you would then immediately be assumed afterwards back in lowercase mode, okay? So the way their coding scheme was designed was it was this complicated mess, I didn't design it, where you have certain characters in each mode, just like on the iPad keyboard, and certain commands you could send to either temporarily go into this mode or permanently go into this mode. Okay? And this meant that for any given message, there were many, many possible ways to encode it. You could type capital Skina as Shift Skina, go back into S, go back to lower mode, Shift K, go back into lower mode, or you could hold Shift Lock down and type S-K-I-E-N-A. Does everybody see those are 2 different ways to type the same thing? Right? And which is it that takes less movement? Okay? In this case, to store the message, each one of these characters or shift commands took a certain number of bits. Any message could be expressed in many, many different ways, depending upon whether you want to permanently shift into a mode or temporarily go there. Okay? And the compression algorithm is to find the shortest possible encoding for any string. How many people think they understand the scheme here? Okay, any questions? If so, then these people at Symbol, okay, came to me, one day, and they were saying, look at this, we have this great barcode thing. We use all these heuristics to find the best possible encoding, okay, because we really want to find the shortest possible encoding for any message so we can fit the longest prison record possible on that back of that driver's license, okay? But I said, wait a second. Why don't we think of this as dynamic programming? Let's let Mij be defined as the minimum way to encode the first I characters of the message ending in mode J. Okay? This is the string position. This is the mode number. Does everybody see here? There were four, it looked like 4 modes. Okay? The message was n characters long, right? The cheapest way to encode the first I characters ending in a particular mode was what? It was the minimum over all possible modes, okay, of doing the first I minus 1 characters, ending up in the kth mode, and then encoding the ith character and shifting or ending up in the jth mode. Does everybody see what the situation is? Okay, there are 4 possible modes you can possibly be in at some point, right? M sub ij is, we're defining it as the cheapest possible way to encode the first I characters and end up in the jth mode. Okay? So what do we know? If we got to end up in this mode and encode all these characters, either we could have been in this mode before, in which case mi minus 1j was the previous way of getting up to the last character, and then pay the number of bits it takes to encode the last character, right? Or we might want to have previously been in another mode, then shift into this mode and encode a character, or encode a character and then shift into this mode. Does everybody see that the cheapest way to get in to end up in mode J after encoding I characters is the cheapest way? We were in some mode before we were doing the ith character. It was the cheapest way of encoding the message ending up in that mode, plus the cost of getting out the last character and ending up in the mode that we want. Okay? And this is exactly the problem that we are looking for. How many people understand this? How many people don't see it? Any questions about that? Okay, now again, there's this detail, the messy part of the barcode standard is all hidden in this magic word cost of this. This is the messiness of the barcode standard, right? But the underlying idea is as simple as this, okay? There are only a small number of modes. The optimal way to encode the message ends up in some mode. Which mode do I want it to be in at the end of the encoding? I don't care, because I have nothing else to encode. After you've typed in your name into your text into iPad, you care whether it's in capitalized mode at the end or not? The caps lock button is down. No. But you want the cheapest way of all possible ways, ending in any possible mode. And if you compute for every possible prefix the cost of ending up in every possible mode, you will have this. Any questions about it? If there are a total of k possible modes, and the text is of length n, What is the complexity of this algorithm? How many boxes are there going to be? Kn, right? And how much time is it going to take to fill a box with this recurrence? Okay? It is looking at all the min over all possible modes, right? So this min is being taken over the k possible modes, really, right? So this is going to be something that is going to run in order n times k, which means order nk squared, which, considering the number of modes in our barcode standard is 4 or 5, means it's like linear in the size of the message. How many people sort of get this? Okay, any questions about it? This is why I say when you see it, it's not that hard. This can't be that hard. Okay, if you look at it. If I tell you that is the solution, it's not that hard. And yet, if you don't understand dynamic programming, you don't see it, right? But I can tell you that the simple people had this very complicated heuristic they were very proud of. And when we then implemented our dynamic programming, it came up with 8% better codes than theirs did. Okay, it increased the capacity of their barcode standard by about 8%. Okay, so you're going to have 8% longer prison records and still have a New York driver's license. Any questions about that? Okay? Any questions about this dynamic programming thing? Okay? Any questions? Let me try one other dynamic programming thing. Unless, okay. Any questions about anything dynamic programming wise? Okay? Let me try one more example of a dynamic programming thing. Another dynamic programming idea. But again, see basically what we're doing, the key elements. We write out what we want our function to be. We come up with a recursive for it. We then analyze it by, we're going to store the results. It's how many cells times the cost of filling in each cell. Okay? Any questions? Let me try one more example. Okay, and hopefully this will take us to the next point. So one other example from the book on that. Again, the way I understand on some level your frustration. You're seeing it, I think. You're seeing that I'm doing something I think is easy. You're seeing that when I write these things out, they're not that long. This is one thing that you should see. The complete answer is short, right? That's a sign that there can't be that much magic there, right? But getting to that point maybe is still hard. The only way I can think of doing it is by looking at more and more examples. That's my understanding. Okay? Any questions? Okay? So let's look at one more example, if we can. Okay? And this has to do with a problem of scanning work, okay, scanning through work, okay, using k workers. Suppose, let's say, we have in this case, a library of books, okay? And the books have a certain number, the books are on an encyclopedia shelf, okay? Or they're on a bookshelf. And the books are ordered, and some of the books are very thin. This is a thin book, right? This is a thick book, okay? And you have a certain number of pages of books to get through. And on one of them, okay, one of the pages, the spy wrote down the secret codes to send off the nuclear weapons, or something like that. There's some secret, or more than that, the key to the combination to get into the vault with all the money. That's even better, right? Now, we want to find where they wrote that combination. And how can we figure this out? You have to look at every page of the encyclopedia of these books to find that out. Does this seem like a reasonable case? Okay? Now, you have k workers, and you want to find the combination as quickly as you can. You want to take the books on the shelves and say, lefty, you take these shelves. Righty, you take these books. Centery, you take these books. Okay? and go through them. Okay? Does everybody get the idea? You can't break the books because the librarian will give you trouble. Okay? You have to partition the books, okay, by dividing the work up, by sort of dividing it. You get A through K, you get K through M, you get M through Z, okay? And our goal is to minimize, to do this in the fairest possible way, okay? Does everybody see that if you have 9 books with 100 pages and 3 workers, this is the fairest possible way? Okay, yes?
Is this K partition?
It may or may not be K partition. Okay, it sounds like it should be K partition, but let's say, I'm not going to say, I don't know, let's say maybe. Okay, we'll leave it at that. Okay? Now here, if I have books where the books get fatter with time, like the Harry Potter series, right? Okay? Would it be the best case that I took those 9 volumes and divided them equally among the 3 workers? Okay? Is the fairest way to do it to divide it like this? 3 books each. Yeah?
No, because the person who has to read the largest number of pages at
This person has a lot more work. This guy has only 600 pages to read. This guy has 2,400 pages to read, right?
I mean, in general, it might not be possible to get everyone an equal.
They can't get an equal thing necessarily. But what would be the most equal way to do it? Okay, yeah?
Can you just see it in terms of number of pages, and then like divide it based on those, not based on the book itself?
Well, okay, so if we agree I can't divide up, I can't split the book in half. We agree we want in each partition the total number of pages to be as equal as possible. The question is, how do we find what is the most equal way to divide it? Yeah?
It would be the partition such that it minimizes the number of pages that any one person has.
Okay, so you're now starting to sound like a dynamic programming person. You're saying it's going to be the one that minimizes what everybody has. Okay, so let's just take a look at it. This, I claim, is the right partition here. Does everybody see on this particular example, this was the optimal solution. This guy has 1,700 pages to do. This guy has, how many is that? 1,500 pages to do, I believe. This guy got off the easiest, but still the worst case time. This guy, although he got the worst, okay, it's not as bad as it would have been otherwise. Yes? Okay, yes. Okay, the answer is here we're saying you cannot switch the order of the books. That will change the problem if you can switch the order of the books. Actually, doesn't make it easier. It makes you can get up with a better solution potentially. Turns out it's harder to solve, okay, but you can come up with a potentially better solution. But here we're not going to allow you to rearrange the books. We're only going to allow you to divide these things up by inserting, you get lefty got A through H, right? You're not allowed to move them. You're just allowed to position them on a shelf in the library for them to start scanning at. Okay? So how do we define the optimal way of doing this? Okay, how do we find the fairest way to break this up? Okay? Any ideas? Okay? Okay, you want a wrong idea for it? Here's a wrong idea for it that's going to be what you guys might think of normally. What if you found the average number of pages in the book? Okay, the average number, you find a total number of pages, and you divide it by the number of workers you have, right? And let's say that in that case, and then you keep going from here to here to here to here, until you get just to the point where it's above or below the average, right? This guy's now got a fair amount of work to do, right? And you then keep going till you get to the next average. Do people see what I mean by this strategy? Okay? And that'll probably find a pretty good partition. But you never know whether you go just above or below the average at any particular book. Does everybody see that? Okay? And that's really kind of what's going to be making that's the limit of that approach. How many people are with me now? You should still be with me here. If you're not with me, I want you to ask questions at this point. Any questions? How do we find the optimal way of doing it? Okay? I claim we're going to use dynamic programming. And how are we going to use dynamic programming? Well, what is it that we want to know? What is M sub I j going to be defined as? I want to claim that it should be equal to the minimum largest piece, right, with books 1 to I and j workers. Does everybody get this idea now? Would this help me? Again, you can't read it, but I'm reading it for you. M sub ij, the minimum largest piece, okay, where you have divided up the first I books among j workers. If you could compute this, would this be a good thing to do? Okay, would this give you the answer? What would the answer be? You would want to do it with all k of your workers, right? And all n of your books. Does everybody see that? So the question is, can we come up with a recurrence relation for where we do this, how we compute this? Yeah?
Well, yeah, we can do this recursively. I mean, just for starters, if we have one book and we have k workers, then we can just give.
So you give me, okay, so you're giving me basis cases, M sub, if you have n books and one worker, what's the optimal way to do it?
Give all books to the one worker.
So that person is going to get what? The sum of all the pages. Let's let P sub I be the number of pages in the ith book, right? Does everybody agree that if you've got one worker, this is what it's going to be? Okay? Any questions? What if you have n workers? What is the right way to do it? If you have n books and n workers, what is the right way to do it? Yeah?
One book to one worker.
One book to one worker, and if you got stuck with the thick one, that's life, right? And if you have more workers, you can't help it right now, because only one worker can hold the book at a time, right? So we also know that M sub nn is going to be equal to what? The max of pi as I goes from 1 to n. Is that right? That says they're basically the thickest number of pages. Okay? Does that make sense? In general, what is it going to be, though? Those are basis cases. Those are good. You got to have them. And maybe it's good to work through them just as a first practice. But now we got to get to brass tacks. What is our recurrence going to be? Yes?
Well, I think you have to start dividing up somewhere. So you can ask which first division will minimize the rest of it with that first one.
Okay, so you say you want to divide it up first. I always think from last. I want to think, what is the last worker going to do? Right? I'm going to say, where do you start the last worker? It's the same way of looking at it. You hold it in the mirror, it's the same way. Okay? But what is the last worker going to do? The last worker is going to be at the kth position. What is the kth position? I don't know, but I do know that it's got to minimize the total cost. So let's say that K is going to be the position of the last worker, right? It could be anywhere from 1 to I, because I is the number of books, right? If I let's make my picture here again. If these are my books, here is I, because that's the ith book, right? If my last worker is here at K, what is the cost of my solution? If I put my last worker at K, how much work will the last worker do? Okay, yeah? Right, the last worker is going to be doing what? The sum, as, let's say, z goes from k to n of pi. Does everybody see that if I put my last worker and divide it up there, the last worker is going to have to do all of that stuff, right? How much will the other workers do? What's the biggest piece the other workers are going to do? Yeah?
That would be m of...
That's my recursion, right? Does everybody see? So what is that going to be?
That would be m of n minus k,
M of, I think to be precise, I'm up to m of k in this case, right? K minus 1. The k minus 1 books among how many people? J minus 1. Does everybody see that this is the cost of all the guys to the left of it? This is the cost of the last worker, right? Does the sum stop at I or I minus 1? Wait, what do you mean by that? This is going to I, because that's picking my k. Oh, this you're telling me should go to I. And this should be P of z, right? Okay? But now, what are the possibilities? Does everybody see that it's the max of these two things, right? I could stick all the work on the last worker, right? And make this thing very big. That means make the thing k very small, right? But then this part is going to be very big. I could go very easy on the new guy. And then all the work's going to be done by one of the, the biggest piece will be done by somebody else, right? I want to put the last worker at the point that minimizes the larger of the two pieces of work to be done. Does everybody see that? This is exactly the same kind of thing we're doing over and over again. Okay? Any questions about that? How many people see it? A little. Okay? Any questions? Okay? Yes?
I'm sorry, what are you maximizing again?
We are minimizing. We are trying to find the place to put the last worker so that it will minimize the total amount of work done. Right? How much work will be done if we put the last workers to give them from the books K through N? K through the end of the books. The last worker will have to sum up all the pages on all those last books, right? What will the other pages have to do? Well, we have J minus 1 remaining workers responsible for the K minus 1 other books, right? And this can be solved recursively, right? Does everybody see that? This is a smaller number, and this is a smaller number than this and this. Okay? So we have made progress, and in fact made progress towards a basis case. Okay? Any questions about that? Okay? What is the running time of this thing? It's the number of boxes times the amount of time it takes to fill a box. How many boxes are there here? N times K, right? And how much time does it take to fill a box? Okay, you got to be a little bit careful. This is going to go around N times. I guess I should switch to the color. This goes around N times. This is looked up in constant time. This is a little dirty looking though, right? This is summing up the number of pages. If I sum it up from scratch each time, how much would this take? I'm summing up N times potentially, right? This could be the number of pages on N books, right? So if I explicitly brute forwardly compute this every time, this would be N times something where it takes 1 plus N time, right? So if I have to compute this sum each time from scratch, this would take order N. N times order N, this would be order N squared per box. If you look at the book and read it, you'll see there's an easy way to avoid computing this sum every time. And so if this sum can in fact be computed in constant time, and if so, then that's n times constant. In fact, this thing can be computed in n squared times k time. And you can read the book chapter for details. Any questions about that? Any questions about this? Okay, I want to, before we go anywhere, I want us to, you have the winners? Okay, so here, I want to quickly, but I do want you to sit through this. We do have our, you will get back your homework 4s later, but we do have the winners here from when we ran the contest. And I want to discuss it just quickly as a last backtracking thing before you go. So there were a total of 6 programs that made the cut, okay, that were submitted, that we were able to compile, okay? And we went through them, and by the time we got to, all of them could handle 15 vertices comfortably, okay? By the time we got to 18 vertices, 3 of the programs were out of the competition. By the time we got to 20 vertices, okay, we had one program that did it in 160 seconds and another that did it in 72 seconds. Okay, so we're awarding the winner to the 72, okay? So let me just go in among the final 3, just for knowing. Timur Robin was 3rd. Who's Timur? Okay, raise your hand. Okay, he was 3rd. Sai-Wing Chen was 2nd. Who's Sai-Wing Cheng? Okay. Silicila Cheng, excuse me. Okay. And the one that came in first was Mike Baruda. Okay, okay. So Mike, come up here. He's our champion for now. Okay. So what I want to do is he will receive a priceless, another book of mine. Okay, so that will be the prize. But let's just quickly go through how did you prune this, okay? And we'll talk just for a data. What did you do to prune?
It's been a lot.
Okay.
No,
okay. Well. Okay. Fine. Tell me what you. Let's describe what you did to prune.
I didn't think I actually would win, so I wasn't.
Okay. Well. Okay.
But well, I tried to. When I was constructing my actual permutation, I tried to figure out as soon as possible. You know, I have, let's say, n possible n vertices. So I try to, what numbers can go into the first element, the first position in the ordering, second position, third position, blah, blah, blah. And I would look to see which possible pairs, if one vertex has, 5 children, then it obviously can't be in the 4th to last position, and none of his children appearing before that. So imagine that you have a vertex and it has 5 children, and none of those children appeared in the first, n minus c, if you say c is the number of children, n minus c points in the permutation, which I'm...
Okay, so I think I now understand his pruning criteria. Let's go through this and see what I think he's saying here. Suppose you have put down this partial thing, right? Suppose you have a vertex here, and you correct me if I'm wrong about what your pruning criteria is. This vertex here has, let's say, degree 5, one of which goes to here and one of which goes to here. Its unaccounted degree is what? There are 3 more neighbors of this that haven't been placed yet. Do people see what I'm saying here? So if this guy is here, he's got 3 more. Let's say this guy has a total of degree 5. If this person is here in the array, our partial solution, what is the minimum size of any bandwidth solution that includes this thing? Well, we know that these edges, there's 3 more that are remaining. The best that could possibly happen for this would be if these guys went ka-chunk, ka-chunk, ka-chunk. Does everybody see that? Okay? And therefore, there is a lower bound on how well you can do from here. Okay? Based on where you have put things so far, where the remaining degree is. Is this the idea that you're using? Okay, does everybody see what he's doing here? Because this is a little bit clever. Okay? He is now pruning, not based on have I seen an edge so far, but whether I am going to see a long edge in the future. That's kind of the interesting thing that I think most people didn't do. My guess is most people pruned, oh look, I knew there was I've seen a long edge so far. This can't be a good thing, right? He can say that if you had one unaccounted edge over here, it's going to imply a long edge, right? Even if that hasn't appeared in your solution yet, it's going to appear. And so he can backtrack now. Is that the basic idea? Do people see this idea? Any questions about that? Do people see how this enables them to predict into the future and prune even before the solution has gotten bad? Because it's going to get bad. Okay? And that's why he won. I didn't do anything so complicated. That was it. Now, how could he have done even better? Okay, if you guys want to stay for that, I know you guys want to leave, but I'm going to tell you how you might have done even better. Another possibility is, everybody insisted, I think, on putting the pieces down in order from left to right. Might it have been better to logically fill in our permutation in vertices like this? Why would that be? Because if instead I put in my element logically in the first spot and the second one in the kth spot, right? If there was an edge here, I would immediately prune. Do people see what I'm meaning here? Let's just go back here. The problem with the idea of filling them in left to right is that you don't get long edges if they're going to be. You don't discover long edges until you put a lot in. Does everybody see that? What if you had filled it in from left to right? We put one here, and then we put our next one here.